Hello everyone, my name is Goran Zuzic and today I'll be talking about universally optimal distributed algorithms for known topologies. This is a joint work with Bernhard Haeupler and David Wajc, and it's a work that is set to appear in STOC 2021. So let's get started. Suppose that we are given some specific distributed network G. So how you should think about the distributed network G? You should either think about some computers in a large network like the internet, perhaps about processors in a supercomputer, or even sensors in a field. Now, these nodes in the network want to solve some optimization problem on the network graph. For instance, you might want to be solving the minimum spanning tree or the MST problem, the single source shortest path, the min cut, or some other distributed optimization problem that comes to mind. Now, during this talk, we will mostly focus on the minimum spanning tree problem, as it is a simple problem that is pretty typical in the setting. Now, as a short goal to keep in your mind, your goal is to design a distributed minimum spanning tree protocol that is as fast as possible until all the nodes compute the minimum spanning tree of that distributed network G. Okay, before we dive into the specifics, let's discuss why do we even care. Why is the distributed optimization even important? Well, to answer this, I'll tell you that the world is becoming more and more decentralized, as all of you know. So an understanding of distributed algorithmics is getting progressively more and more important by the day. Furthermore, from a theoretical perspective, understanding the fundamental barriers that occur in distributed computing will ultimately lead us to design better algorithms. And moreover, having an understanding of the barriers will enable us to tell what is actually possible and what is not possible to be done in a decentralized way. Now, why do we care about the minimum spanning tree problem and not some other problem in this area? Well, the minimum spanning tree problem has been studied to death in the centralized setting for more than 100 years. We think we know basically everything there is to know about the problem. And likewise, it is the most well-known and well-studied problem in the distributed area too. It was introduced by Gallagher, Humboldt, and Spira in 1983. But however, in spite of being introduced about 40 years ago, there are still many important open questions that we actually don't know how to resolve. So, to put it in one way, the minimum spanning tree problem is the easiest hard problem that we don't really know how to resolve yet in the distributed setting. Furthermore, from a practical perspective, there even exists a standardized spanning tree protocol. So it is good to know that actually somebody in practice kind of cares about this kind of things being computed in an actual network. Now, of course, this is a purely theoretical talk, and I do not claim there is any direct link between this and practice. However, it might be possible that ultimately, after combining with many other work, this work being done now might help design better algorithms somewhere in the far future. Now, most of the prior work in this distributed minimum spanning tree area focuses purely on the pathological worst-case graphs. So basically this means there is this one worst-case graph for which you can't really do well, and because of this, nobody really tries to do better on other graphs. However, I don't really think this is a particularly helpful answer, and one can give a better one. I would like to know what is the optimal runtime of the distributed minimum spanning tree and other distributed optimization problems for non-worst-case networks G. So this is going to be our guiding question. Alright, so before we dive into the results, we definitely need to specify the formal mathematical model in which this computation actually occurs. This is going to be the classical CONGEST model, and it is formalized in the following way. Our network topology is abstracted as an undirected graph G. So the vertices of this undirected graph are the computers, and the edges are the links connecting those computers. Communication in this model is performed in synchronous rounds. So you have round 1, round 2, round 3, and so on, and every node is perfectly synchronized and one knows when a round starts and ends. During every one of these synchronous rounds, neighbors exchange polylogarithmic bit-sized messages with each other. A neighbor can exchange different messages with different neighbors. Computation in this model is strictly free. So this is a model that doesn't care about computation, but actually cares about the communication. Like, I want to be able to get as much information about the graph and the input such that I can actually compute the required result. However, even though computation is free, we will not be abusing this fact. And initially, nodes only know their immediate neighborhood. So every node knows the IDs of the computers in its neighborhood and knows the part of the input. So for instance, in the minimum spanning tree, it would know the cost of the incident edges to that node and does not know about anything else of the graph. The objective that we want to optimize is to minimize the number of rounds until all the nodes learn enough about the graph to compute the minimum spanning tree of the entire network. All right. So now let's talk about the background for the distributed minimum spanning tree problem. As I said before, it was introduced by Gallagher, Humboldt, and Spira in 1983, and they gave an n log n algorithm that works on every graph. This was later improved by Averbuch in 1987 to an optimal order n algorithm. Now, why do I say this is optimal? Because you could theoretically have a path graph, so something that looks like this, where you have n edges between the leftmost and the rightmost endpoint. So now, if you use less than n rounds, the leftmost and the rightmost endpoint would not be able to even hear from each other, hear about their parts of the input. So clearly, for a global problem like the distributed minimum spanning tree, you should not be able to do anything without at least n rounds. Now, this argument can normally be generalized to the following one. If you have any graph G, you need at least diameter time to compute the minimum spanning tree. So why is this the case? It's completely the same as I said before. So if you have two nodes that are diameter apart, you will need at least d rounds until these two nodes are actually able to communicate. Without d rounds, you will not be able to hear. And d obviously stands for the diameter. Now, knowing that actually diameter is an important parameter, Garay, Kutan, and Peleg develop a more fine-grained algorithm for this setting that works in n to the 0.613 about plus diameter many rounds. And of course is the number of nodes in the network. And now, clearly this is kind of better than the optimal algorithm because now we started parameterizing by the diameter too. And here you should think of the diameter as the small number, and you should think of n to the 0.613 as much larger, because in a typical network of interest, the diameter is polylogarithmic, while n to the 0.613 will be huge. Furthermore, this was then improved by Kutan and Peleg to square root n plus d algorithm that works on every graph. Now, curiously enough, Peleg and Rubinovich proved a few years later that actually there exists one pathological worst-case graph for which you cannot do better. Specifically, that graph has a diameter of log n, so small, but in spite of the small diameter, it needs square root n rounds to actually compute the minimum spanning tree. So in some sense, this is tight on the worst case graph. You cannot do better. You can do square root n plus d everywhere, and you need square root n on this worst case graph. So in some weak sense, the square root n plus d algorithm is optimal if you look at all the graphs. Now, after many years of stagnation in this line of work, the next one that I like to point out is the work of Ghaffari and Haeupler in 2015 that actually proved that on planar graphs one can actually do better. On planar graphs you can actually solve them in diameter rounds. Now, since there is a lower bound that says on every graph you need diameter rounds, and there is an upper bound that says that, well, on planar graphs diameter rounds is enough, clearly this is the best possible result. On planar graphs, you cannot do better than D, and you can do D. I mean, on every graph you cannot do better than D, but here this is like a planar graph is an example where we actually have good algorithms that works in optimal time on them. Furthermore, this was then later extended by Haeupler, Izumi, and me to genus-bounded and tree-bounded graphs. There exists an order D algorithm for them, and later by Haeupler, Lee, and me that you can do on minor free graphs a diameter squared algorithm, which was then later simplified and improved to an order D algorithm for the minor free case. Now you could see that those bounds are matching only for the worst case graph and some special graph classes like the planar graphs and the genus bounded graphs and tree bounded graphs and minor free graphs. So this actually raises a very natural question that was posed by Goran and Pelig in 1993, and that is to close the gap for every graph G. More specifically, you give me a graph G and you ask me what is the graph parameter that characterizes the distributed complexity of the minimum spanning tree problem and other problems. Furthermore, do there exist universally optimal algorithms that are as fast as possible on every possible topology, so those that actually match that graph parameter that determines the distributed complexity? We answer both of these questions, so that's the big reveal. So let's dive into these results a little bit more precisely. Well, the graph parameter in question is the so-called shortcut quality of G. Now this parameter was actually defined in prior work by Ghaffari and Haeupler in 2015. However, it wasn't really clear, it wasn't known at all back then that it had anything to do with the lower bound, and it also was not known that it actually works in every graph G. So, for the lower bound, or the impossibility view, we proved that the distributed minimum spanning tree takes at least shortcut quality of G time on any graph G. So any correct algorithm needs shortcut quality time to compute the correct result. Furthermore, from an upper bound, so that means an algorithmic view, the distributed minimum spanning tree can be actually solved in shortcut quality of G time if the topology is known in advance, but not the input. So now here, I would like to point out that we kind of changed the model on you a little bit. So we assume two things. One, that every node knows the topology in advance. However, the nodes do not really know the input in advance. So the input here in the minimum spanning tree problem is the edge costs. So every node in the beginning only knows the edge costs of its incident edges, but not of the rest of the graph. Well, this known topology is a little bit simplification in the upper bound case, and we do need current to this simplification, but we do believe it can be alleviated in future work. Furthermore, even the lower bound is actually harder to prove in this known topology case, because whenever you get more information, the lower bound gets harder. But I would like to point out that we actually do this, and we prove the lower bound in the known topology case. So we kind of close the gap completely in the known topology case, and we also believe that this actually closes the gap in the general case, but this is currently a conjecture. So what are the consequences of this result? Let's talk a little bit about this. Well, we achieve universal optimality, which means that we give an algorithm that is as fast as possible on every network. You can intuitively think about this as an algorithm that perfectly adapts to the network at hand. And this is, of course, currently achieved in the known topology setting. The previous notions of optimality that were talked about were so-called existential optimality. That means that a graph is optimal in a class of graphs. So, for instance, when I said the result of order n is optimal, I kind of meant that it is existentially optimal when parameterized by n. Furthermore, the square root n plus d result is also existentially optimal, but this time with the parameterization via n, the number of nodes, and d in the diameter. You could arguably continue this proving existential optimality with an ever-increasing set of parameters until you don't want to do it anymore. However, if you ever prove a universal optimality result, you would cut to every parameterization because a universally optimal algorithm is optimal with respect to all possible parameterizations. So this is like one notion in which universal optimality is very much better than the current versions of optimality that were present in prior work. Now these results can actually be applied to other problems. I did talk so far about the minimum span each, and I'll continue to talk mostly or exclusively about it, but we actually provide a very general framework that actually works for the approximate distributed shortest paths, approximate distributed min cut, distributed connectivity verification, and other problems. And for all of those problems, the shortcut quality of G characterizes all of the runtimes. So actually, you could think about this problem as forming a new complexity class, because all of these problems that I said kind of introduce to each other. So you can think of this like a new complexity class that contains the shortest path, the single source shortest path, the minimum cut, the minimum span tree problem, and all of them form a new complexity class that wasn't observed before. And they, on every graph, they have a runtime of the shortcut quality of G. All right. So far, we have treated shortcuts as a black box. And in this section, I'm going to tell you what are shortcuts and what is the shortcut quality. And then I'm going to tell you a little bit more. I'm going to give you intuition why the shortcuts are actually connected to distributed algorithms. Okay, so let's start with the shortcut definition. We are given a graph G, and inside this graph G, we are given different connected node disjoint parts. So, as I said, we are given a graph G, and inside this graph G, there are different connected node disjoint parts. Now, the idea is that those parts, which are subsets of nodes, want to facilitate communication internally. So basically, the nodes inside the part want to talk to each other, but not to other parts. In order to do this, you might think it might be a good idea to talk only inside the part. However, the diameter of the isolated diameter of the part itself might be very large because the part might be windy, and in particular, it might be much larger than the diameter of the entire graph. So what we are going to do, we're going to help the parts by adding new shortcut edges that would reduce the diameter. So to every, let's say, part P1, I'm going to add some shortcut edges like this. That the idea of these edges is to reduce the diameter of P1. Now, after that, I could actually do this, let's say the diameter is Q. I could build a BFS tree of this part with the shortcut edges and facilitate communication within time Q. However, the problem is that we are actually doing this for many parts at the same time. So, when you actually do this with respect to some other part, P2, you might use some edge multiple times, and that's actually not something you want to do. You want to bound the congestion, so that means the number of times that the edge is going to be used. So now this kind of leads to our definition of shortcuts. We say that a shortcut is of quality Q if both the diameter of every part is at most Q and no edge is used by more than Q times. So every edge is used by at most Q different shortcut edges. All right. So now this is defining the shortcut for a set of parts. Let's define the shortcut quality for a graph. And it's just the worst case shortcut quality over all possible set of connected and node disjoint parts. So what does the definition tell us? This max just tells us to take the worst case possible set of parts. And this says, well, for the worst case possible set of parts, just take the best quality shortcut. All right. So now, after we define this is a very combinatorial object, the shortcuts. And now we are going to tell you what does this have to do with anything in distributed algorithms. Now, I'm going to define you the following somewhat artificial looking problem that is going to make sense a bit later. This problem is called the part-wise aggregation. It was defined by Goran and Haeupler in 2015, and it says the following. Well, it starts by having the same notion as we had before. We have a graph G, and inside this graph G, we have a set of parts. So we have this set of parts, and the parts, as I said, want to communicate internally. And they want to do it in the following way. So every node has some private input xv. So the node v has a private input xv. And now all the nodes in some part want to find the minimum or the sum or some other simple function of the private inputs in its part. So this part here wants to find out the minimum of all the private inputs of the node in this part. This part, other one, wants to find the minimum of all the nodes in its own part. Once you find this out, you say that you have solved the partwise aggregation task. Now, the claim is that if you are given a shortcut of quality Q, then you are actually able to solve the partwise aggregation problem in order Q time. And naturally, this shortcut needs to be defined with that set of parts that you are solving. Now, why this is the case is kind of maybe might be clear to you. Well, if you have like one part only in the world, you are able to communicate internally via that shortcut edges of that one part only. And since the diameter of the shortcut edges of this part plus the shortcut edges is small, you can do this fast. However, this also does not take into account the congestion, so you do need to be careful how you actually synchronize different parts such that you do not incur congestion on any particular edge. Now, we do control for it, but it's still not super clear how to do it. However, a very standard so-called randomized delay trick will make short work of this problem. I will not go into the details, but I will leave the hint on this slide. And if you would like to know more how this randomized delay trick is done, you should stop here the video and read more about it. Moving on, let me tell you why this actually has to do with the minimum spanning tree and how we can use shortcuts to solve the minimum spanning tree problem. Now, first thing, what we want to do is to be able to construct different shortcuts in different parts. We call this the construction oracle, which we give a set of node disjoint parts, and it spits out a shortcut of quality Q. Naturally, this oracle needs to be distributed, so it is given input in an appropriately distributed way, so the set of parts in a distributed way, and it will output a shortcut also in the appropriately distributed way, which I will not define here. So the claim is that once you have a construction oracle that always spits out a shortcut of quality Q, you can solve the minimum spanning tree problem in order Q time up to polylogs. And the proof for this is you just run the most natural Borufka's algorithm, which is a classic algorithm to solve the minimum spanning tree problem. Since the algorithm is so simple, I will actually tell you how it works, which I'm sure most of you will know already, but let's say it one more time to be on the same page. So in the first step, every node V finds the minimum outgoing edge out of that node V. You add that edge to the minimum spanning tree, you contract that edge, so all of the nodes V do this in parallel, like at the same time, and you repeat the steps for log n times. So let's be a bit clear. So every node, so you have a graph, every node V starts contracting other nodes around it, and they contract this, and eventually, let's call this contracted supernode apart, P1. And the different nodes do this at the same time. P2, and so on, P3. So as you can see, these parts or this contracted supernodes are obviously node disjoint and connected, and that's kind of what motivated the definition from the previous slides and the shortcut definition. Now, the thing that you want to find in every step of that algorithm is inside every contracted node, you want to find the minimum outgoing edge. Well, this is exactly the partwise aggregation problem, and you can use this to find this in order Q time. Now, I claim contracting the edge, you might think that might be a problem to do in a distributed fashion, but I claim it is not. It can be done with very standard tricks, and that part you can do quite easily. Of course, after repeating this contraction trick for log n times, in every round the number of parts goes down by a constant factor, and after log n time steps, you will actually end up with one part, and the MST and all the edges that you ever found are going to correspond to the MST of the entire graph. I am now going to give a high-level technical overview of both the upper bound and the lower bound of the paper. So the claim is, for the upper bound, that if we can construct shortcuts efficiently, then we can solve the minimum spanning tree in shortcut quality time as we wanted. So the question is, can we actually construct shortcuts efficiently? We show in this paper that the answer is yes. But currently, we only know how to do this in the known topology setting, and this is why we need the known topology assumption for the upper bound. The question, however, is far from easy, because you can think about it in the following way. The challenge is that different parts of the graph need to communicate internally amongst themselves without knowing what the other parts of the graph are. So one part needs to communicate without knowing what other demands for communication are in the graph. Well, you can actually learn a little bit about other parts, but not too much, because you need to be efficient, and during a small number of rounds you can only learn a small amount of information about other parts. You definitely cannot learn all about other demands and parts. So this is even a challenge in the known topology setting, because even though you know the entire topology, you do not know what other demands exist in a graph, what other parts of the graph want to communicate within themselves. So one way to go about it is to make the problem even harder. Let's say we don't want to learn, not only we say we can't learn much about it, let's learn nothing about it. Now, you want that every part of the graph that wants to communicate with itself is completely oblivious about the other parts of the graph, but you still want to be able to get near optimal solutions. This is so-called the oblivious routing problem that has been studied mostly in the literature. So we try to utilize this oblivious routing, and that's the way how we actually go about this. However, in our setting, we need to balance both between the diameter and congestion, whereas standard oblivious routing solutions only optimize for the congestion. So the problem with this is that standard solutions fails. We need to take into account both the diameter and the congestion and jointly optimize between them. This is a completely new problem for which the standard solutions don't really work. So we actually solved this problem in a separate paper called the Hop-Constrained Oblivious Routing. And in case you're interested in hearing more, check out the paper or the accompanying talk on YouTube. This paper is also set to appear in STOC 2021. So putting these things together, we have the following theorem for our upper bound. Suppose that all nodes know the topology of G up front, then we can construct shortcuts of near optimal quality Q in order Q many rounds. And consequently, we can also solve the minimum spanning tree in shortcut quality rounds. We now turn to the lower bound side of things. In order to prove the lower bound, that you cannot solve MST faster than shortcut quality time, we will first go through an intermediate problem called the distributed disjointness task. Alright, so what is this task? It is a two-player game between Alice and Bob. So you have Alice and you have Bob, and they are both given a k-bit input x and y. So Alice is given its own k-bit input, let's say 0, 0, 1, 0, and Bob is given its own k-bit input, let's say 0, 1, 1, 1. Now, this game is actually played on a graph. So we are given k node disjoint paths, p1 to pk, so paths in the graph. So let's say path number 1 looks something like this. We have path number 2, path number 3, and path number 4. They are no disjoint. And Alice controls the heads of these paths. So Alice controls, let's say, these nodes. These are the heads. Whereas Bob controls the tails of these paths. And by controls, I mean it can see all the stuff that the nodes receive, and it can also tell the nodes what to send in the following round. The question is, what is the minimum amount of rounds until both Alice and Bob can decide whether their inputs are disjoint or not? So we say that two bit strings are not disjoint if there exists such an input I, such an index I between 1 and k, such that the ith bit of the Alice's input and the ith bit of Bob's input are both 1. So in this example, the third bit, this one, of Alice's input, and the third bit of Bob's input are 1, so they are not disjoint. The problem does not ask us to find a particular index, but it's simply a yes-no decision question, where both of them need to find out are they disjoint or not. How they do it, well, the particular index you don't really need to find, you just want to answer yes or no. Now, the theorem that we prove is that this distributed disjointness task is very intricately connected to the shortcut quality. Particularly, given a set of paths P1 to Pk, if you can solve the distributed disjointness task on every subset of these paths in Q rounds, then you can also find the shortcut of quality Q for this set of paths. And this is an if and only if condition. One side, that if there exist shortcuts of quality Q, you can solve the distributed disjointness task, is relatively easy, and you can see this if you think about it. However, the other task is somewhat more surprising. Why? Because in order to say that you cannot solve a communication problem of distributed disjointness, if there does not exist these combinatorial objects of shortcuts, seems to be a hard thing to prove. Because yeah, you're bounding a communication problem via a combinatorial property. However, this kind of results are known in network theory, network coding theory, and information theory, and they are called network coding gaps. And because of this, we proved such a network coding gap for this problem in a separate paper called Network Coding Gaps for Completion Times of Multiple Unicasts. It's a joint work by Bernhard Haeupler and David Wajc that appeared in Fox 2020, and a talk is available on YouTube. And I would advise you, if you would like to know more how you actually prove this network coding gaps, how do you bound a communication task by a combinatorial property, I would advise you to see the talk or the paper. Alright, so we go through this distributed disjointness task as an intermediary. Okay, now let's talk, when we have all the ingredients in place, let's give a high-level overview of how this proof actually looks like. What we would like to prove, one more time, for the lower bound, is that the time to solve the minimum spanning tree problem is up to polylogs more than the shortcut quality of G. Now, how do we actually prove this? Suppose that there is a very fast MST algorithm that works in Q time. First, we show a reduction that using the MST oracle, we can solve the distributed disjointness problem. Furthermore, using the network coding gap from the previous slide, we then argue that if there is a good solution to the distributed disjointness problem, there is a good shortcut quality. So this is actually how the lower bound works in its entirety. I will now give a more in-depth overview about how the lower bound actually works. So the statement that we would like to prove is we want to show that the time to solve the minimum spanning tree on any graph G is lower bounded by the shortcut quality of G up to polylog factors. Now, equivalently, we can state it in the following way. So, given any set of connected and non-disjoint parts, P1 to Pk, we can construct shortcuts of quality order TMST on them. Alright, because that's kind of the question. If you construct on any set of parts a shortcut of quality TMST, then assuming the TMST is small, you get small shortcut quality. Perfect. The first idea that I would like to observe is that we can actually assume that the parts are not general node subsets, but they're only paths, like SITI paths, which have a much simpler structure. So we state the theorem in the following equivalent way. Given any set of non-disjoint paths, P1 to Pk, we construct TMST shortcuts on them. Alright. So the question why this holds, I'm not going to go much deeper in it, but the idea is to use a heavy light decomposition and then just apply the path theorem to construct general shortcuts on any general parts. If you'd like to know the details, I actually put some hint on the next slide. So feel free to stop here and see how it actually works if you're interested in it. Moving forward, the question is, how do we actually prove it? How do we construct the MST shortcuts on a set of paths? The thing that helps us here is the following definition of a disjointness gadget. Okay, so the definition says a disjointness gadget of a set of no disjoint paths P1 to Pk. So here it's going to be, we have this set of paths P1 to Pk. Is a connected subset of edges, denoted here in blue, that touches every head and every tail of all of those paths, so head and every tail of all of those paths, but does not otherwise intersect the interior. So F does not intersect like the interior of those paths. Perfect. Now this is not really the full definition. It has one exception, that you're also allowing constant many exception intervals of small order d length on each one of those paths, and I will allow you to intersect F inside of these exceptions. However, for now, it might be a little bit conceptually easier if you just ignore this for now and just imagine that it does not intersect the interior. Handling this exceptional intervals is relatively straightforward. Okay, so now the question is, how do we use these disjointness gadgets? The observation here is that if you have a disjointness gadget on a set of no disjoint paths, then using a single call to the MST oracle, you can solve the distributed disjointness task on P. Alright, so why does this observation work? What's the idea? Well, assume you want to solve the distributed disjointness task. So Alice and Bob get inputs X and Y. I'm going to tell you how do you assign the minimum spanning tree costs such that when you call the minimum spanning tree oracle, you get a cost of 0 if and only if X and Y are disjoint. Alright, so that's kind of what we're trying to do. So this is what we're going to do here. First off, to all the edges in F, so all the blue edges, you are going to assign a cost of 0. Okay, so all the edges in F, you're going to assign a cost of 0. Furthermore, look at every one of the paths, P1, P2, and so on. And now in each one of them, to all the edges except the first edge and the last edge, you're also going to assign a cost of 0. Alright, same thing on the other paths. All 0, all 0, all 0. And finally, on the first edge on each of the paths and the last edge of each of the paths, you're going to assign the Alice's and Bob's inputs. So for instance, on the first edge of the path, you're going to assign the Alice's input x1, x2, and so on, up to xk. And on the last is going to be similar, y1 to yk. Now, the idea is, if there is an MST of cost 0, that it cannot happen that any one of those paths, for instance this one, it cannot have a cost of the first and the last edge of 1. So if this is a 1 and this is a 1, the MST cost cannot be 0. It must be more than 0. So if the MST cost of 0, each path has at least one xi or yi to be 0, and therefore they must be disjoint. And similarly, it has a cost of more than 1. There must be at least one pattern that have a common 1, and therefore they're not disjoint. So that's it. That's the entire idea. So if you can find disjointness gadgets, you can solve the distributed disjointness task on those set of paths. So now the big question is, how do you actually construct the disjointness gadgets? And this is actually where the main technical contribution of the paper is, because given a set of no disjoint paths P, I claim that there exists a disjointness gadget of large size. With large size means the size is 1 over a polylog factor of the original set of paths. However, finding it is fairly technically involved. Now, suppose that we assume we know how to find them. Let's see how do we complete the proof. Well, it's fairly straightforward and conceptual, so let's go through with it. So, assume the theorem. So our task is to construct shortcuts of quality TMST on an arbitrary set of no-disjoint paths P. What do? We find a large disjointness gadget on a large subset P prime of 1 over polylog fraction. Because this is a disjointness gadget, using the theorem from the observation from the last slide, we can solve the distributed disjointness task on this set of paths P prime in T order TMST time. Using the network coding gap result, we now know that there actually exists good shortcuts on P prime of quality TMST. And finally, we have the good shortcuts on this P prime. We remove P prime from P and remember the shortcuts and repeat this polylog many times, each time finding a shortcut for a 1 over polylog fraction of the paths, finding the shortcut, remembering it, removing that, and repeating. Since in the end you kind of take the union of all the shortcuts you ever find, I claim the quality of the final shortcut it only increased by a polylog factor, so it will have a quality of order TMST. So that is it, that's the entire proof. Alright, after you have internalized the rest of the proof, the main thing that is remaining is how to actually construct these disjointness gadgets. So, as I said before, constructing the large disjointness gadgets, such that when you're given a set of no-disjoint paths P, you want to find the disjointness gadget on a 1 over polylog fraction, that's hard and technically involved. However, I can show you now some intuition about how to get a little bit weaker result, the one where you get 1 over an order D fraction of the paths. So here is how it goes. Suppose that you have those set of original no-disjoint paths P here on the down left. And the procedure is like this. First, what we do is we choose an arbitrary root R. So just choose an arbitrary node. Let's put it here. And call it the root R. Okay. So now, let's consider what would have happened if we add some path Pi to our set of disjoint gadget paths P prime. So let's say that this is our path Pi. And what do? We take a walk from the head and the tail to the root via some shortest path of length at most order D. You can clearly find such a thing because the diameter of the graph is D. So we come and you take a walk towards the root. So it does something like this, and then it intersects possibly some other paths, and eventually it reaches the root. And clearly you kind of do the same thing from the rest, from the tail. Okay, so what do? We add these two walks to F, which, good, that makes sense. We add this to F because, we want to have this F to be a one connected component. So since it's connected to, all of them are connected to this root R, they're going to form one connected component if we can actually do this properly without intersecting the interiors. Okay, so this walks that we want to add to F intersect some other paths. So what do? We would just delete them. So in this example here, well, we would just say, well, let's delete this one, first one, and the second path. And we will not deal with them in the first, in the call, we will just delete them and deal with them sometimes later. All right. Now, the last thing that is a little bit of a problem is that these two walks that we started from a path Pi might intersect the path Pi itself. Now, we do have a little bit of leeway. If you remember, we can actually have a constant number of so-called exceptional intervals on each one of those paths. And if those intervals are of small length, at most order D, we can allow this F to intersect those exceptional intervals. Now, so clearly what you want to do is you want to say, well, since in the beginning and in the end the walks can intersect the path, you want to say, well, let's pronounce this an exceptional interval. And this is completely fine, but it might happen that the exceptional interval done in this way might be too long, because we actually at the end want that the exceptional intervals have a length of at most D. Right? So let's say, so if they have a length of at most D, then you pronounce them exceptional intervals and you're complete, and you would be done with this. However, it could happen that this is obviously not the case, and in this case we do a little bit of switching. So what does that mean? It could just so happens that there is a very short path, like order D, right? But it kind of intersects, so this is at most D, but it doesn't, but the thing that we want to pronounce the exceptional interval has a length of much more than D. In this case, well, there is a very simple solution. We can just switch it around. We can say, well, take the last intersection of your walk from the head to the root with the path and pronounce that part as the actual new version of the path. So you would have a new version of the path that goes like this, and this part you would completely discard. And now you actually can pronounce this an exceptional interval because it has a length of at most D. So after the switching, you can pronounce an exceptional interval, and now you can actually connect to the path and you can actually connect to the path. Okay, so this actually kind of ends the story on what would have happened if we were add to pi to the set of the jointed gadget paths p prime. Now we never really actually did it because those paths could delete each other that we would choose. But there is a very simple argument that you can actually choose some subset of them that do not delete each other. The main step here is to just see that every path pi deletes only order D many other paths. Well, this is clear because those walks have only order D length. So and each hop of the walk deletes at most one or two other paths. So clearly it's going to be at most order D. So what do? You can make a very simple argument that you can find an independent set P prime of paths that is at most of size 1 over order D of the original set of paths that do not delete each other. So that is the complete proof. This is kind of how you fix the construction up to an order D factor. So now let us conclude and give some open questions. Nothing like this was known before, as in the only universal lower bound that was known before was the trivial diameter one. So here we showed that shortcut quality is a universal lower bound. And we also show that it can actually be matched. So there exists algorithm that work in O tilde of shortcut quality time, which actually gives the first universally optimal algorithms, but currently only when the topology is known. Now the obvious natural conjecture is to prove that actually you can do this on every graph. And for this, you actually only need to show that shortcuts can be constructed efficiently, or near optimal shortcuts, so quality Q, can be constructed in order Q time up to polylogs. This would actually give a characterization for every topology, so in the usual CONGEST model where you do not know the topology, and would give universally optimal algorithms in every graph. Now, there are many connections of this work to other fields of theoretical computer science, because it's kind of a new result, and to work upon it we needed to develop tools for many different areas of TCS. So to give a few examples, these include new network coding apps from information theory. These include new types of oblivious routings from like graph theory and approximation algorithms. And also these include new connections between distributed computing and communication complexity. And now the nice thing here is that not only do we draw from these areas to prove our result, but the line of question is asked in this paper kind of influenced new results in those other areas, and now there is kind of a mutual benefit because the questions lined in this line of work benefited the other areas because we were able to solve some questions there that were, I would say, notable and nice. All right, so the open questions remaining, well, we can pose a bunch of them, and they're kind of natural. Are there universal optimal algorithms in other models? So, for instance, what about when you worry not about the time, but about communication complexity? Or you worry about both time and communication complexity jointly. Can you have both? Can you be, universally optimal in both? And what would that even mean? Or maybe you want to be just with respect to time in the CONGEST broadcast model, or in the radio model, or some other model. So that is kind of a way, develop universal optimality in other models. And the other question that I'd like to pose is also a very natural one. Can you have universally optimal algorithms for other problems? So here we show that it works for like distributed minimum spanning tree and approximate shortest path and approximate min cut and so on. But for instance, we do not know anything about exact min cut or exact shortest path or any other problem that comes to mind, all pair shortest path, which I don't believe even the shortcut quality is the right answer, but it should be something completely else. All right, so that will be it, and thank you for your attention.